we are going to just quickly review what we talked about as modulation chirp. So, in the last few lectures we have been saying that we have to use a laser instead of LED if we were to go for higher modulation speeds, but higher modulation speeds will give rise to what we call as a chirp. Chirp meaning the instantaneous frequency changes, and the instantaneous frequency change can have two consequences. One, based on where you are biasing IB, so based on the power output of the laser PB, so this is power versus current, based on the power, based on the current you will have a certain carrier density, and as you change your IB the carrier density changes. So, when the carrier density changes, refractive index changes, and when the refractive index changes you will have a change in the center frequency of the laser. And we discussed last time how you can make use of this fact. But what is more dangerous is also, so this kind of change is a static shift. I change my bias, so the center frequency, this operating frequency changes. So, we call this kind of chirp as adiabatic chirp, okay, adiabatic chirp or a static chirp, because there is nothing time varying here. It is based on the bias current and it is based on a fixed bias current, and as I set bias current changes, my answer changes, my center wavelength changes. So, this first consequence what we have calculated here also in this example is called as the adiabatic chirp. Essentially to say that the carrier density adiabatically changes, and so you have a change in center frequency. But the second one which we discussed last time, where if you have a current modulation, which means that N is now a N as in carrier density, we were using capital N. So, capital N carrier density also changes with time, which leads to refractive index changing with time, and that leads to a phase modulation, and that is transient chirp, right, because it is continuously changing with time because my modulation is a time dependent function. And in order to represent or quantify the transient chirp, as I said, this is a measurement that is typically done, and it is quantified through what is called as a line width enhancement factor. Henry's line width enhancement factor. Henry probably was one of the very first people who defined this to quantify the change or quantify the phase modulation because of intensity modulation. So, as I said earlier, look, we were intending to do only intensity modulation, but as a consequence we have phase modulation also. And the real problem is the phase modulation becomes a problem for a communication system because phase modulation leads to spectral broadening, right. So, the spectrum, if you see delta f, which is 1 by 2 pi d phi by dt, instantaneous change in phase is your frequency, and you have quantified d phi by dt. So, I have written it as 1 by 2 pi alpha h by 2 pb dp by dt. So, this is how you can quantify how exactly the spectrum changes when you have a given intensity modulation. So, it is important, it is the deciding factor is this alpha h, and that is a measurable quantity. And I said last time that this value ranges between 4 to 6 or 4 to 8, it is a dimensionless constant. Now, watch out, there is dp by dt. So, as your modulation speed increases, you are doing a 1 gigahertz modulation versus a 10 gigahertz modulation. Higher modulation speed would mean that a larger rate of change, and a larger rate of change would mean that larger delta f, the spectrum will start broadening. Okay. So, both the chirps are together quantified. So, we can quantify what is called as a total chirp, which is first part is the adiabatic part or the static part, and the second part is the time varying part, right. So, this is how the frequency of a laser changes because of the current. Okay. So, here you see it is dependent on PB, and this part is 1 by 2 pi alpha by 4, it is the same term written here, but you have taken alpha h by 4 pi together. So, 1 by PB dp by dt. Okay. And to keep this out constant, you multiply it with one constant kappa. So, this kappa is your adiabatic chirp factor, and you have the line width enhancement factor, right. So, there are two factors, two constants you should know for a laser. And this kappa, the adiabatic chirp factor, so this kappa is your in fact, I gave you in the last problem I gave you a number for not kappa, it actually I gave you a number for alpha h kappa by 4 pi, that whatever percentage change we said, right. But what is typically quantified in a data sheet is this adiabatic chirp factor, and that number, some value for is that for a practical laser. Of course, depending on the structure of the laser, whether it is a quantum dot laser or a quantum well laser, or depending on how you are making the laser, the kappa could slightly change, but these are some orders of magnitude, 20 terahertz per watt inverse. If you have 1 watt of power, of course 1 watt of power is a large power out of a semiconductor laser. So, we are talking about milliwatts of power. For milliwatts of power, so you can say that it is 20 gigahertz per milliwatt of power. Okay. So, that is the order of magnitude you would have got in that calculation also. But that is static chirp, but as dp by dt changes. So, for instance, if I have a current that is modulated as Im sin omega t, I will have a power that is modulated as Pm sin omega t, and if we make an assumption that this modulation frequency is below the resonant frequency, so that there are no nonlinearities in the system, I know now what exactly my dp by dt is, and I can substitute that and then figure out what is the spread. Mind you, this spread is different from the spread because of modulation. So, there are different spreads that we are talking about. First spread is because of the line width of the laser, that is coming because of the resonator, quality of the resonator. Then when I am modulating it with, let us say, so this is the carrier frequency omega c, let us say. When I am modulating with a tone, let us say 10 gigahertz, right, a single tone of 10 gigahertz, I will start getting these side bands at omega c plus 2 pi into 10 gigahertz, and I will have omega c minus 2 pi into 10 gigahertz. This is because of modulation, just because of the fact that I modulated it with 10 gigahertz. What is this adiabatic chirp delta f that we are talking about? This should happen at the center frequency. So, if that adiabatic chirp is coming out to be, let us say, 2 gigahertz, it means that the center frequency, instead of your starting center frequency, which could be, let us say, megahertz laser, let us say we are picking. So, instead of megahertz, this will now start to become, of course, the total energy has to conserve. So, if I am plotting it in the same scale, the center frequency will now start looking like this because of the chirp, which means that these modulations will also start having that width. Because of the fact that you modulated, the center frequency has changed, that is what it means. And you really do not want this in a communication system, because the larger is your spread, more will be the effect due to the chromatic dispersion. Okay. So, this is one thing to watch out for when you are doing direct modulation. You should always ask this question: how much is the modulation, the spread in frequency because of the modulation chirp, and can that be tolerated in my system? So, when you are ultimately going to do a link design, which we will come to, you will start thinking about these aspects of the laser. Okay. Maybe if it is a short distance communication, it may not matter, but again it depends on how much is the chromatic dispersion and how much is the allowed spread and so on. Okay. So, now we move on to other non-idealities of a laser So, this is just to summarize. In a direct modulation, you can have high frequency limited by relaxation oscillation, and I also told you a technique to push the relaxation oscillation to a larger frequency. All what we need to do is to increase the power, which may have different consequences, but that can reduce the nonlinearities by pushing the relaxation oscillation to a larger frequency. And of course, we talked about frequency chirp now.